Thank you for joining this NIOSH 50th Anniversary Science Webinar, Behind the Science, Spotlight on NIOSH Field and Laboratory Research. Today's webinar highlights 3 NIOSH scientific activities that occurred in the field in our research laboratories. It's the 3rd webinar in our series celebrating NIOSH's 50th anniversary. Congress passed the Occupational Safety and Health Act of 1970 that created NIOSH to assure that, as far as possible, every working man and woman in the nation safe and healthful working conditions. The act was signed into law on December 29th of 1970, and NIOSH began operating on April 28th, 1971. Today's presentations reach across multiple industries, span work over many decades, and represent NIOSH's collaborative efforts with industry, workers, academic, and government partners. We hope you enjoy these presentations. You're going to hear topics today on seismicity research to improve mine safety, chemical, biological, radiological, nuclear, respirator research, the practice, and identifying a workplace hazard from inhaled butter flavoring vapors, the diacetyl story. Our disclaimer for the material that you're going to see today, the findings and conclusions in this presentation are those of the authors and do not necessarily represent the official position of NIOSH or CDC. Our speakers today are David Hansen from the Spokane Mining Research Division, myself from the National Personal Protective Technology Laboratory, and Ann Hubbs from the NIOSH Health Effects Laboratory Division. Our first presenter today is David Hansen. David is currently a senior advisor to NIOSH Spokane Mining Research Division. He received his PhD in geophysics from the University of Colorado in Boulder and began his career in mining research at the U.S. Bureau of Mines. After a break from federal service, David recently returned to the mining field at SMRD as a team leader. He is currently involved in research dealing with geophysical aspects of mine stability and safety. And with that, welcome, David.
Thank you, John. Good morning or afternoon, everyone. As John mentioned, I'm Dave Hansen, and it'll be my pleasure this morning to give a brief description of NIOSH's efforts in seismicity research as related to mine safety. Get the next slide, please. The first thing I'd like to do is define what constitutes mining-induced seismicity. As mining progresses and rocks removed from the ground stresses redistribute. These stresses can arise from gravitational loading or tectonic stresses. When that stress is greater than the rock strength, the rock will fail, and it does so sometimes very violently, and a mining-induced seismic event occurs. The bottom 2 figures shown here show the sort of ground vibrations that we typically analyze. Now, not all mine seismicity is bad, and it is normal and even healthy in mines. But some patterns or types of seismicity indicate that the ground mass is reacting in a way not anticipated in the mine design. One of our goals is to distinguish between these normal stress adjustments and seismicity that presents a hazard. In terms of evaluating mine safety, the questions that we address include: what are the specific failure mechanisms? Where do these events originate? And are the vibrations strong enough to result in damage? The primary aim of our research is to use seismicity monitoring to identify conditions that contribute to mine hazards and provide guidance to mitigate that risk. We approach this by correlating mine seismicity with geological and geophysical properties that may lead to increased seismicity. Finally, the result of this work is to evaluate and to develop methods for assessing that risk that can reduce worker exposure. Ultimately, we strive to help mines maintain clean, safe openings, as shown in the photo on the right, as compared to mine openings that have failed and result in dangerous situations, as in the left-hand photo. When working underground, It should be remembered that all mine openings eventually close. This closure may occur within hours, days, months, or years, but no openings remain indefinitely. Seismic monitoring allows us to evaluate how the ground is responding to mining and how rapidly and in what manner this closure might occur. As shown here, even foot-square wood pillars underground will eventually crush and collapse. Modern mines constitute complex engineering structures and are not simply a hole in the ground. As shown in this rendering of a deep metal mine, mine openings, like shown in gray here, are really complicated 3D structures. They wind down into the earth and allow access to the ore. But the earth is not a uniform building material like concrete or steel, and mine engineers must adapt their designs to accommodate both known and unknown structures and risks. A major reason the deposits even exist where they do is that the geology is complex, faults and other structures exist, and thus the ground is potentially unstable. Seismic monitoring allows an evaluation of how and where stresses and unsafe conditions are developing in a three-dimensional sense, whether there's worker access to those areas or not. In this figure, the yellow spheres show the location of seismic events and how they relate to mining and mine structures. Monitoring this seismic activity can be used to confirm design appropriateness, stress concentrations, seismic activity levels, and in some cases provide sufficient warning to allow evacuations. But it's not only increases in seismic activity that can present hazards. It has been observed that when normal background seismicity quiets down, miners tend to start to worry because that could mean that stress is accumulating and a big event is imminent. Understanding seismic behavior and how it relates to overall mine safety constitutes a major technical challenge. Some seismic events are immediately hazardous to miners, while others, if they occur far from active workings, do not. Research into using mine seismicity to understand mine failures has been pursued since at least 1945 with work from the U.S. Bureau of Mines. After the Bureau was shut down, this work continued at a reduced level until the former Bureau of Mines Mining Research Division was absorbed into NIOSH. Now, obviously, techniques have made major advances since that time. Results that took days to produce are now available in near real time, providing more accessible information. NIOSH utilizes seismic sensor arrays that are installed both in underground mines and on the surface. SMRD currently has networks installed at both metal and coal mines located in the western US. As shown in the top photo, networks consist of an array of seismometers that detect ground vibrations. In that upper photo, you can see there are yellow triangles, which are the locations of seismic sensors deployed over an underground mine. Each of these sensor installations consists of a vault for the seismometer, solar panels for power, and radios for communication. One of these vaults is shown in the lower photo of this figure. Detected vibrations can be mining induced, they can be local or remote earthquakes. We have detected nuclear test explosions and even the motion of ocean waves. Events associated with mines are now automatically processed, and the locations of these events computed and plotted, providing rapid access to summarized data. Through advances in our understanding and in advances to computing power to process data, significant progress has been made in processing and visualization of seismicity. Seismic events are processed using a combination of automated algorithms, machine learning, and manual interpretations to determine their location and size. Easy to understand interactive plots are provided to mines in near real time, allowing them to assess potential seismic risks. Representative plots, such as the one shown here, show the magnitude, location, and temporal history of the mine seismicity. Mine operators can then use these risk assessments to take precautionary measures. Even with the major advances made in understanding why and when seismic events occur, we're still working to provide better information to mine operations. We're investigating new sensing technologies that will allow easier deployment and a better understanding of the impact of seismic events on mine safety. One of these new technologies are nodal seismometers, which are about the size of a 1-pound coffee can with built-in GPS receivers, and these can now be used for short-term, high-density array monitoring in areas of particular concern. The right-hand photo above shows one of these nodal seismometers being installed over an active coal mine. Other sensors, like distributed acoustic sensors using fiber optic cables as continuous vibration monitors, allow denser coverage and a better definition of seismic activity. These fiber optic sensors also have the potential to detect other factors besides ground motion that impact health, safety, and mine stability. Now, despite advances in technology and improvements to worker safety, mining remains an inherently hazardous occupation. NIOSH research continues to better understand the role of seismicity in overall mine stability and risk assessment. As technology and understanding advances, we're actively building on the body of existing work to facilitate seismic monitoring, offering safer work environments to the mining industry. To thank you for your attention. If you have any questions, please enter them into the Q&A chat. And I'd like to turn it back to John for our next presentation.
Thank you, David. I'm John Sola. I've been with NIOSH since July of 2001, and I'm currently the Deputy Director for the National Personal Protective Technology Lab located in Pittsburgh and Morgantown in our facilities there. I've been in the personal protective technology business for most of my career, starting with the work with the Department of Army, and now with the working at NPPTL over the past 20 years. In thinking about today's presentation, in preparation for today, that this year marks the 20th anniversary of the terrorist attacks on the World Trade Center, the Pentagon, in Shanksville, Pennsylvania, and I think it's appropriate that we remember and honor those who gave their lives and the workers who risked their lives and their health in the rescue and the cleanup efforts following those attacks. NIOSH has played an important role and continues to play an important role in addressing workers' needs in the aftermath of these attacks. I think one of the things that if you're interested in these types of efforts that NIOSH has undertaken, you can find the information on those topics on the World Trade Center topic page. What I'm going to talk about today is specifically related to the journey that NPPTL went on in relation to evaluating technologies for respiratory protection against potential terrorist threats, and coming up with respirator certification standards that could be used to assure that those types of devices protected emergency responders when dealing with those types of emergencies. Over the past 2 decades, we have developed a systematic approach that identifies the hazards that the responders could face. We've assessed the capability of respiratory protection equipment to see how they provide protection against viable threats through benchmark testing, and we've set certification standards that have stretched the capabilities of the technology. And these all lead to enhancing the protection that is offered to responders that they may have to face during the CBRN event. The bottom line is that our standards development and certification programs conducted in PPTL have led to an increase in the national inventory of NIOSH approved respirators that have CBRN protection capabilities. The NIOSH research into the specific needs of responders actually began with a workshop held at Morgantown in 1999, a couple years prior to the events of 9/11. That we partnered with the Department of Defense and the Occupational Safety and Health Administration to conduct this workshop to look at the range of areas in which advancements to protect responders were needed against terrorist events. The assessment of the type and magnitude of respiratory threats potentially faced by responders led to the establishment of test representative agents and test concentrations that NIOSH uses in testing to assess the capabilities of the respirator protecting responders from likely threats. Our work that was done prior to 9/11 demonstrated that neither industrial nor military respirators provided a full range of protection against the known or anticipated CBRN terrorist threats. The development and implementation of test procedures since then, along with minimum performance requirements for construction of respirators, have enabled us to establish the approval program criteria that we use to evaluate equipment today, and that gives us assurance that the requirements that we've defined in our standard will provide equipment that will meet the anticipated threats that could be seen by responders. In response to the challenges of the situation at the time and the desire by our user community for performance, these criteria include performance tests where we challenge the respirators with chemical warfare agents, where we use a third-party lab at the Department of the Army to conduct those types of tests for us. And these have led to the work that was done, in the early part of the program led to the establishment of several different types of respirator standards that are used and still continue to be used by responders today. So in addition to our actual approval of respirators, our respirator approval program includes both pre and post-market activities, which are activities that are conducted either before or after the respirators reach the market. And I'm going to go into that in a little bit more detail in the next few slides. This schematic indicates one of the tests that is done with our third-party test lab at the Department of Army, where a mannequin with a respirator mounted on it is used to evaluate the performance of the respirator against the chemical warfare agents. So for the respirators with CBRN protection, our pre-market activities included developing the design and performance requirements of the respirator, as well as also developing test methods that were necessary to evaluate different performance products of the respirator. For example, right now we're currently working in partnership with the National Fire Protection Association in developing respirator standards, which include CBRN protections for a combination unit respirator, which includes self-contained breathing capabilities as well as air purifying capabilities. Our approval process consists of a thorough review of the manufacturer's quality management system. We also evaluate the respirators using NIOSH standard test procedures, which were developed as part of the standard development process. And these include the chemical agent testing that I referenced that use sarin vapor and sulfur mustard vapor and liquid for challenging the construction of the respirators. We also evaluate them for laboratory respirator protection level, which assesses the ability of manufacturers' user instructions for the wearer to properly prepare, don, and wear the respirator, and as well as assess the fit of the respirator to the user's face. Now, we also use this test to make sure that the respirator fits a wide range of facial sizes and dimensions. One other key aspect of the approval program is that we've adopted, or we use different national, international standards to help evaluate the respirator performance, which include things like durability, environmental conditioning, breathing resistance, the field of view, how well you can see while you're wearing the respirator, communications for making sure that there's clarity, when you're talking or trying to communicate wearing the respirator, and then things like fogging, that the lenses don't fog while you're wearing the device, and that you can be able to don these types of products and then also be able to train with them. And so our post-market activities that we include with our CBRN program also include annual and product and site audits of manufacturers' facilities and products. We investigate field issues that are identified by users or by manufacturers, as well as issues that are covered with as part of the NIOSH firefighter fatality investigation program. While not necessarily part of CBRN, the NIOSH CBRN SCBA, self-contained breathing apparatus, are widely used in the fire service, and any issues associated with injuries or fatalities by firefighters, we're part of that from an evaluation standpoint of evaluating the respirator. We also post public announcements of recalls, retrofits, or revocations of approval as they may occur in the process. And then also another post-market activity unique to CBRN includes reviewing and identifying current and emerging CBRN threats that may pose a risk to the emergency responder. And this is what I'm going to talk about during the latter half of my presentation. In 2016, we received funding from CDC to conduct an updated CBRN hazard assessment. We've always considered that the CBRN standard is a living document, and a commitment that we made to our emergency responder partners at the beginning of the program was to periodically review the protections that the standard affords and then make modifications as appropriate to assure that the respirator continues to protect against the range of potential CBRN hazards. We initiated this updated hazard assessment in 2016, and the project was completed in 2018. And we worked with our partners at the Department of Defense and Department of Homeland Security on this project. I think looking at historically at our efforts, we have hundreds of NIOSH approvals for CBRN protections, at least through earlier this year, and we continue to process and evaluate applications as they come in. This is this graphic indicates the steps that were taken during the hazard assessment. And what this means to the end user is that we use this template to conduct our hazard assessment that can be used either periodically or on demand to address emerging threats, and use this to assure that our test procedures represent contemporary hazards. I think that one of the key elements of our 2018 hazard assessment was that we found that our testing that we do as part of the approval program continues to represent the potential respiratory threats that a responder may see from a CBRN event. The other aspect of this that was important is that we were able to expand the list of hazards that the responder may see in an event, and to be able to include that in our list of protections. So a responder would know that his respirator is performing against a wider array of potential respiratory hazards. Where we've been in the last few years, we initiated a follow-on study to evaluate some high priority chemicals. Well, we felt there was a need for testing of existing CBRN canisters against different chemicals that were on our priority list. And those types of evaluations have shown that the canisters perform as intended against the hazards that were identified. We also undertook another activity with DoD and Homeland Security to expand on the work, the hazards that were identified, to be able to look at illicit drugs and their precursors and apply the same methodology for how we did the hazard assessment to the identification of the potential hazards, from this continuation of the work. And that work continues, at least with regard to developing a framework for how respiratory protection and other aspects of PPE could be selected for protection by responders. The work our project team was well received. We won the Bullard Sherwood Award for interventions in 2020, and also we were recognized by the Mid-Atlantic Federal Laboratory Consortium for the work that was done in partnership with our other federal partners to be able to address this project. Some of the things that you can look for, at least in terms of resources with regard to these types of respirators. We're in the process of updating our webpage to include relevant resources like science blogs and fact sheet. We did have a publication that was in the Journal of Occupational Environmental Hygiene that documented the results of the 2016 to 2018 hazard assessment. And that's being used to update other NIOSH publications that have been assembled over years, like our certified equipment list, respiratory protection handbook, and then also a CRC handbook of respiratory protection are all being updated to reflect the new technology and the evolution of the performance of these types of products. And I think in summary, I think the CBRN story definitely tells a progression of how we used research to evaluate the technological capabilities of respirators. Use that research to develop a conformity assessment and approval program process, for evaluating the performance of these types of products. But then we also established a longer term, post-market reflection of these types of devices to assure that as we move forward into the future, that we have a consistent methodology to be able to continue to evaluate these products and improve upon the performance requirements that we set, for these types of devices. So with that, we're going to transition to our next presenter. And our next presenter is Ann Hubbs. She is a veterinary medical officer in NIOSH's Health Effects Laboratory Division. She's also a faculty member at the West Virginia University, board certified in veterinary pathology, and a co-author or author of more than 100 peer-reviewed papers specifically dealing with respiratory and toxicologic pathology. Her studies have included many emerging workplace hazards, including nanoparticles and flavoring vapors, and she's received numerous awards. And according to Scopus, her publications have been cited more than 6,000 times in the scientific literature, and this has given that an H index of 39. In addition, she's used her knowledge to respond to public health emergencies, including the anthrax events in 2001, the monkeypox outbreak in 2003, Hurricane Katrina in 2005, and then also COVID-19. So with that, I'd like to welcome Ann.
Well, thank you, John. And I'm going to try sharing my screen here. So today what we are going to talk about is the story of how what started with a workplace investigation that was intended to help one workplace ended up helping multiple workplaces. Next slide, please. And so this began with a health hazard evaluation, which is a NIOSH on-site investigation of workplace disease. In this case, it is an activity that is specifically authorized in the Health and Safety Act of 1970 that actually created NIOSH. The reason for that health hazard evaluation was because a physician reported severe lung disease in 8 young workers. And so the investigation began with a request that went initially to OSHA. But after going to OSHA, there was a request for a NIOSH investigation because OSHA found no known hazards. What was truly surprising was that the workplace that requested this made microwave popcorn. Next slide, please. That's a picture of the actual plant. So the question we asked was, how could something in a microwave popcorn plant cause lung disease? The investigation began by considering the ingredients. And the ingredients were corn, salt, oil, and butter flavoring. But we know that corn, salt, and oil are frequently used in workplaces. Those workplaces don't have a lot of disease. And corn, salt, and oil aren't in air. These workers had lung disease. But butter flavoring that is in microwave popcorn is not exactly butter. And so we asked the question, what's in there? And we started with, what does the production of the butter flavoring look like in a microwave popcorn plant? And this is a picture of the mixing room in a microwave popcorn plant. You can see the large vat of oil, and the flavorings are added to that to make the final more dilute butter flavoring mixed with oil. And looking at the vapor phase that would reach the lungs, our colleagues at NIOSH in Cincinnati performed GC mass spectroscopy to examine the many different compounds that were actually present within the vapor phase. And one of those was the compound diacetyl. You see there at the front, and Tara, if you can click, I think we'll circle the diacetyl. And diacetyl is the essence of butter flavoring. It's in butter, but it was in much higher concentrations in the microwave popcorn butter. And not only that, it tended to accumulate in the vapor phase. And so the story continued. Next slide, please. Looking at lung function in the workers in that original Sentinel plant, the lung function measured as FEV1, which is the forced expiratory volume produced by someone in the first second of exhalation. When that was compared with the cumulative diacetyl exposure, as diacetyl exposure went up, the lung function went down. Let me show you a representative image from a worker. Next slide, please. This is a graph of the lung function of a worker who worked in the mixing room. And you can see that over time, which is on the x-axis, the worker's lung function continued to decline until, Tara, if you can click, he left employment, at which point he did not improve, but the rate of decline decreased somewhat, so he was somewhat stabilized. Next slide, please. It's important to realize that field studies and investigations of workplaces are absolutely critical for us to understand associations, but particularly with a complex mixture, as in the vapors that were present over the butter flavoring in a microwave popcorn plant. There were actually hundreds of total chemicals there. To see causation, it requires laboratory studies, and NIOSH was very fortunate that at the time of this investigation, there is a new state-of-the-art laboratory located in Morgantown, West Virginia. Next slide, please. So the question again was what component caused the damage, and we looked back at the GCMS spectrum, and diacetyl was actually a suspect, and was a suspect because of its chemical structure. The chemical structure of diacetyl, next slide please, is one that includes a carbonyl group. And carbonyl groups are important because they tend to be reactive. And we'll show what they react with a click. And they tend to react with other compounds. And that's because the double bond actually involves electrons that are moving in a different orbit. Now, when there is a second carbonyl group next to the first carbonyl group, we call that an alpha dicarbonyl compound. Next slide, please. And diacetyl has an alpha dicarbonyl structure. You can see in the middle, there are two carbonyl groups, those double bonds to oxygens, and they're right next to each other. That makes the electrons even less stable. Now, I'm not a chemist, and I'm not going to try to show the exact movement of the electrons, and you can't do that in PowerPoint anyway, but it's easiest to think about that as dancing electrons, and they're just looking for their dance partners, and they're out there in the cells. So I think of it as moving electrons that are dancing through the structure, and with one more click, you can see what that structure is. This is the part of the molecule we were very worried about. Next slide, please. So what actually happens with butter flavorings containing diacetyl and with diacetyl itself is the exposure, and we'll do another click here, to diacetyl or a butter flavoring causes the cells to die. There is a reaction that is going on, and let's do a couple more clicks. And the cells begin to die. And let's click again. What happens when the epithelium lining any structure goes away is that a scar tends to form. And a scar is excess fibrous connective tissue. Within an airway, you lose the dynamics of the airway and it becomes fixed. Next slide, please. This is actual data. These are scanning electron micrographs, first of a normal airway, then a diacetyl exposed airway. You can see in the exposed airway that there has been a loss of the lining. Looking at another control, we see the same thing higher up in the airways, the specific targeting of the epithelium that lines the airways. Now, this is the butter flavoring containing diacetyl. We next did exposures to diacetyl alone. Next slide, please. In a normal lung, there is a nice gentle carpet of airway epithelium. In the diacetyl exposed lung, however, you go from having normal epithelium that is a smooth carpet, and if you click, we can see that, and there are intact cells. With diacetyl, on the other hand, there is cell loss. So that was what we saw in the SEM. That's what we see in light microscopy. Next slide, please. So with repeated exposures conducted by colleagues at the National Institute for Occupational Safety and Health to diacetyl, we see this structure, the arrows pointing to it. It's a proliferating mass of fibrous connective tissue obstructing airflow. And then looking at another butter flavoring that shared that same alpha dicarbonyl group, we see fibrous connective tissue and almost no airspace in this airway. Next slide, please. And there are marked similarities in those changes to the changes we actually see in the lungs of workers. You can see the two arrows on the left are showing what should be the epithelial lining. And between there and the next arrow on the right, you see this mass of tissue. That is scar tissue, fibrous connective tissue obstructing air passages. Next slide, please. Oh, sorry. So there's marked fibrosis in a narrow rigid pipe. It's a bottleneck. So how could that happen? Well, our hypothesis was that it was protein damage. We know that cells are important. Our body is made up of them, and we think of genes as being critical, but in fact, genes are just made of DNA. And DNA just acts as a template to produce RNA out in the cells in our body. And the RNA can then go and move out into the cytoplasm. And it is the RNA that is a template for protein. And it is in fact protein that actually does the activities that allow the cell to perform its functions. That's what we thought that was going on. And we thought it was because of that alpha dicarbonyl group. Next slide, please. What normally happens in protein quality control, and click please, is damaged proteins, which are quite toxic, can be picked up and identified by a molecule called ubiquitin, shown here with the UB in turquoise. Those damaged proteins with their tags then move to a special structure called the proteasome. It's an organelle in the body that then is able to take that damaged protein, move it through and produce in its place the amino acids that can be used to produce replacement proteins and maintain protein quality control. But there is also an alternative pathway. And in that pathway, you take the damaged protein, which is also identified by ubiquitin at a different linkage. And there, the damaged proteins are sequestered in a molecule called sequestosome 1. And in sequestosome 1, with its gathered up damaged proteins, there is then movement to the lysosome. And within the lysosome, they are digested in a process called autophagy. But unlike the recycling that tends to happen in the proteasome, in the lysosome, it's more like the things go out with the trash. So the data we actually had, next slide, please, showed us what was happening. In the airways of diacetyl exposure, as in normal cells, there are lysosomes. They're shown here in green in this airway from a diacetyl exposure. When we then looked for ubiquitin in a normal lung, in a normal airway, you don't see aggregates of ubiquitin. It's distributed faintly throughout the cells. But with diacetyl exposure, we had these strong red fluorescents. Combining the two images, we can see that the ubiquitin has moved to the lysosome. So the red on top of green gives you the yellow that's in the slide on the right. So there had been alterations in protein quality control. Next slide, please. When we looked at free ubiquitin, which is the main mediator of all protein quality control, uniquely with the exposures to diacetyl in the airways, there was a loss of the actual free ubiquitin, that those bars on the far left, the 9 kilodalton bars, you can see free ubiquitin was depleted, depleting the essential methods for controlling protein in the airway epithelium, hence their death. And so the final epilogue to all of this, next slide, please, was not just that we solved the problem in an airway, but the disease that we originally investigated, or NIOSH originally investigated, that was the field group. I'm the laboratory group, or there was a laboratory group I was involved with. That disease was bronchiolitis obliterans, and it was subsequently reported in workers exposed to diacetyl in chemical manufacturing. Next, it was then reported in workers exposed to diacetyl in flavoring manufacturing. Next, it was then reported in workers exposed to diacetyl in other forms of manufacturing. And finally, NIOSH was able to issue a criteria document for a recommended standard so that such exposures could be stopped. And there were other lung diseases that were controlled as well in the criteria document on occupational exposures to diacetyl and 2,3-pentane-dione. Most recently in the laboratory group, we have identified airway toxicity from another structurally related compound, methyl glyoxal. Methyl glyoxal was found to be an emission product of e-cigarettes. Next slide, please. I was just part of the laboratory team. I want to thank Kathleen Kreis and Kristen Cummings for the slides and the data regarding the workers and the workplaces. And I wanted to thank the numerous colleagues involved in taking what began with a simple workplace investigation and ended with things that have helped workplaces throughout the world. I think we now go back to John.
Yeah, thank you very much, Ann. And I agree, Lou. Thank you for my fellow panelists for the great presentations. We have a couple minutes for questions. I'm looking in the chat to see if there's anything there, from any of the participants. We had a couple of questions that were provided in advance. I guess one for David. How do mines use the seismic information that is provided?
Well, typically they'll take a look at where the
Yeah, David, you broke up in the response.
Oh, okay, sorry. They will largely take a look mostly at the location and the magnitude of their seismic events. This will give them an idea of where they want to keep miners out of. There have been cases where they'll pull miners from a particular area when the seismicity is accelerating or the amount of energy that's released is going up.
Okay, thank you, David. I have a question for Ann. Ann, why do you think no one realized that the diacetyl vapors were a hazard before the NIOSH investigation?
Well, that's an interesting question. And actually going back and looking at workplace investigations for about 20 years, well before the investigation of that one workplace, there had been reports of obliterative bronchiolitis and other types of fixed airways disease, particularly in flavoring manufacturing. But those are very complex workplaces with many different chemical compounds, thousands of them. And many of them had not been investigated for toxicity. So I think we have to give tremendous credit to the great teams in the Division of Respiratory Disease Studies, now RHD, Respiratory Health Division, that did a great investigation of something that had been a problem probably for 20 years. But they were certainly helped out in that there was one main flavoring there, and the essence of the butter flavoring, diacetyl, was just one unstudied compound. There were hundreds of compounds there, but it was, to those of us who are trained in toxicology, immediately a suspect. Much easier than going through thousands of compounds.
Thank you, Ann. Yeah, I think we have probably less than a minute left. I think we'll go ahead and start, wrapping this session up. Again, thank you for everyone for your participation, and thank you for bearing with us while we work through some of the challenges at the beginning of the meeting. We're going to continue having activities celebrating NIOSH's 50th anniversary through the balance of 2021. Please continue to track what's going on our 50th anniversary webpage. And that's provided on the slide. Again, the presentations today were recorded, and those will be posted at a later date. So with that, I'd like to thank Tara Hartley for organizing our session, and Ann and David for joining me in the webinar. And thank you all for your attendance, and we'll look forward to seeing you at a future NIOSH webinar.